So I'm going to talk about minimizing carbon in multifamily systems because, well, because that's what we've already been preparing to do for quite a few years now, and now we're just kind of taking it to the next level. We've been minimizing the energy use of buildings for, gosh, I don't even know, 15, 20 years. I don't know how long passive house has been in this country, but it's been a while, and we've gotten a lot of stuff figured out, but there's always places for us to go. And I think that carbon accounting is our next kind of big unknown area. A couple of years ago it was dehumidification, then it was domestic hot water, and now it's carbon. So I also want to make a plug for getting out of your comfort zone and getting into other movements as well, because this is how we kind of multiply our impact. So that's CNUA. I don't know how many people are familiar with the Congress for New Urbanism, but it's all about creating walkable, lovable places, and we all know that where we build our buildings and what they're doing is just as important as how much energy they're using, because the energy that we're putting, the people that we're putting in the buildings is actually the most important thing. So let's make buildings that are loved, and let's make the places outside those buildings with the way that they shape space. Let's make it loved too. So now to get into to drill way down. So so I directed this large research project, and Matthew Fisher at my office would help me out with the using IESVE. And if any of you have used it before, it is a sprawling, crazy program that has a million little levers on it, and to make it do things right is quite a feat. But so we went through and we analyzed. There's four different mechanical systems, 5 different ventilation systems, and 5 different domestic hot water systems that we analyzed for the energy, and then for the embodied carbon of the systems and the refrigerant and everything we could put our hands on. Of course, there's some assumptions we made, and because we have to. At this point in time, we can't really account for everything embodied, because there's so many things that aren't being accounted for right now. We don't know how much carbon equivalent we're really using in all these pieces of equipment and all these materials. It's so hard to figure it out. But so we made a bunch of assumptions, and we used the ICE database and the GWP 20 numbers, and we used that stuff to get as close as we could. And so the analysis is done at a 20-year time frame, and for simplicity, it's a good life of most systems last at least 20 years, but they don't all last more than 20 years. So I thought it was a good life cycle to put on it. So all the numbers you'll see, well, the EUI numbers for energy use intensity are yearly numbers, but all of the carbon numbers are all for 20 years. So this building it's a really cool building. The existing building is a synagogue, and it's phenomenal. And they did a 3D scan of the interior of it, and they found that it's even more incredible than they thought. Like the way that there's intersecting circles going on in the architecture is just it's really, really cool. And that's being turned into a theater, but that's a long way off. The building actually, the apartment building is actually an L-shaped building. Behind, you can kind of see it in the picture, and behind it's 2 stories of new above 2 stories of old. And so there's a lot of carbon already captured in this building because it's an existing building. So I probably should give so it is a passive house building, and it's under construction. It's probably about 80% done, and it has although I saw Terrence on the call. Maybe he knows the more accurate number for that. But the building's 45 apartments and 57,000 square feet. And so on to the heating and cooling, and I'm just going to jump right into them. So the first system we analyzed was the heating and cooling was a variable refrigerant flow system. So this is VRF is the is the acronym. I'm gonna try to say all the real words, not just acronyms the whole time. So this is the system that's in the building. So we have every piece of equipment, all the ductwork, all the insulation, everything. We've got it all. We know exactly how much of it's in the building. So all these numbers are, the exact numbers. I'm not going to read them off or anything like that, but with VRF systems, the leak rate is higher for refrigerant because there's so much refrigerant piping, so many braze connections that, I mean, we've heard horror stories of the whole refrigerant charge leaking before the building even opens, stuff like that. So VRF definitely has a lot. I mean, 214 pounds of refrigerant is a lot. The second system is mini splits, and so we went through and we figured out exactly what the system would look like, and how much refrigerant piping was in it, how much refrigerant is in it, and the leak rate on a mini split system is a little bit less because each unit has only one line set. So, and if anything does leak, it's only in one system. So you have a little bit less leak rate and you have less than half the refrigerant in the piping. Geothermal, complicated system, not to be taken lightly, but the refrigerant all lives inside the heat pumps that are in each room. So you don't have any field brazing or anything like that. So the leak rates are lower and there's less refrigerant because it's all in a packaged piece of equipment. And then the darling of the hour, the all-in-one system. So this is like the EPOCA, which we get calls about EPOCAs every single day now. I don't know why they get it. I don't know how everybody gets our name, but everybody asks us how to use them. And Minutair is similar, but uses a different sort of idea to accomplish kind of the same thing. And they each have their strengths and weaknesses, but they use only a little bit of refrigerant, a lot like because it's all in a packaged system, so there's no split. It's super simple. There's just not much ductwork. There's a lot less stuff. And when you use one of these machines, because it just sits near near the exterior wall and has its louvers right outside. So it requires a little bit different architecture of the building, but you can get a lot of savings in cost too. Even though the unit's more expensive, all the installation's a lot less. But so their leak rate is low for refrigerant too. So here are the results. So I don't know if I said anything about the mental model yet, but creating those shortcuts in your head to kind of get you closer to the solution, not necessarily all the way there, but you always want to analyze this stuff. But it's good to know kind of the relative impacts. This is for this is in Pittsburgh, so it's kind of that in-between climate where there's a lot of cold days. The days get pretty cold, down to 2 degrees, less than 2 degrees, and so it's a mixed climate. There is cooling, but it's not as heavy as the heating. So some of these systems will perform better in warmer climates, and I'll go into that too. So VRF, it's good. It does well with energy. So on the left is the energy use intensity per year of these different systems for this specific building. So VRF does pretty well. Mini splits, they're still decent. I mean, all of these are decent systems. These all meet Passive House. They're all totally electric. It's just that the numbers are still very comparable to each other. It's not like one of them is like, oh, I don't want to use that because it's using so much energy. And also, here, there we go. That's perfect. So yeah, mini splits are, they're okay. Geothermal is really good with energy, and the EPOCAs are a little bit not quite as good with energy, but they're comparable with mini splits. But they don't have the super low temperature ratings that mini splits and VRF and geothermal have. Like they use electric heat below 5 degrees. So that's why actually you're seeing that. You see it actually in the red down there is the heating energy, and that's really where you're getting the hit, is from the electric resistance backup heat. And so the center is the 20-year carbon impact of and yeah, the numbers really don't matter, right? These numbers are all relative. Like the absolute numbers aren't the important thing here. They are when you go through and you do the analysis and then you put it into the whole building analysis. But for the mental model, the numbers aren't super important. It's more which ones are higher than others. But so the center graph is for a fairly dirty grid. This is Pittsburgh's grid. It's got a lot of coal in it and natural gas and things like that. And the one on the right is the grid just north. It's in New York. It's it's a much cleaner grid because they got a ton of wind because it's on the Great Lakes. So it's just they've got lots of wind and they're using it, and it's great. They're doing that, and the grids will all kind of head that way as more renewables get added. But you can see that the relative carbon impact changes as the grid gets cleaner because different things become more important, or they become more of the carbon pie. So VRF, it looks pretty good when you have a dirty grid because your operational carbon is the biggest piece of the pie. But as the grid gets cleaner, or you add solar batteries to your building, the refrigerant becomes more of an impact. So all of a sudden, when you have a clean grid, VRF starts looking pretty bad for carbon because of all the refrigerant that's leaking into the environment. So you can see that the trend actually changes. So you can see in the clean grid scenario, the all-in-one EPOCA unit actually does really well with carbon because it's using very little refrigerant because it's a packaged system. So yeah, so those are that's kind of, you can see. So the red is refrigerant and the yellow is operational, and the embodied of the actual machinery, which I almost forgot to mention, is the blue, because it's fairly low. The mechanical systems aren't that heavy, so they don't have a lot of embodied. There isn't a lot of embodied carbon in the actual machinery. It's mostly in the refrigerant and in the energy that they're using, which makes sense. I mean, we're powering the buildings, or we're conditioning the buildings. So, and also something I also want to mention about this is that in order to normalize this so that we're just analyzing heating and cooling, we took out the ventilation. Well, we made the ventilation all the same for these. So these are all the three systems, the VRF, mini splits, and geothermal, are all using a small room by room ERV that kind of because it's very similar in performance to the one that's in the all-in-one EPOCA system, because we try to normalize it all so that it's easy to see the actual differences. So on to, well, I probably already said all this stuff, but the reason that we chose VRF for this building was just that we couldn't really use geothermal. It just geothermal didn't make any sense for financial reasons, and it often doesn't for passive house multifamily. Like geothermal, it makes a lot more sense for kind of crazier buildings, like, I don't know, say a hospital or an off-grid wellness retreat, or the kind of wilder systems, or systems where energy is king. Like you have to reduce the energy as much as you can. Those are there isn't it. Financially, it doesn't really work. Geothermal doesn't usually work for multifamily buildings. And also with geothermals, you really got to be careful. You got to make sure you got someone really good to install that system, because it's underground, and if something's wrong with it, it's really bad because you just can't make it work right if it wasn't installed properly. So there are some people who do it really well, and so make sure you get one of those guys on your team, or girls. I don't know if there's any girls. I haven't met any. I haven't met any geothermal girls. Maybe that should be something that we work on. All right, dehumidification. So I told you earlier that we split the we took the ventilation, we took the like essentials ventilation out, because that's really the real purpose of those systems in a putting a giant ERV on your roof, or energy recovery ventilator on your roof, is so that you can control the humidity at the ventilation air. So we got five different systems here, and this is the most common one. You see this one everywhere. We analyzed it for Trane, but Daikin, Greenheck, Aon, they all make the exact same thing, like almost exactly. They sit on the same curves and everything. So they are a package solution. So they're nice, but you're adding a lot of ductwork. You're adding ductwork, down chases, through hallways, and there's other ways to do this too. You can do it, floor by floor and little neighborhoods of them. But it's a package system, so it's the compressor and everything is all right in it. So you're not gonna get a lot of leakage from it. You don't have a whole lot of refrigerant in it, but you have a lot of extra ductwork for any central system. So the second system was we split apart the dedicated outside air system. Everybody's seen the Swegon. Everybody's talked to the Swegon people, and the Ventacity and those the fancier ERVs with the higher efficiencies. They don't have packaged versions of those yet. I don't know. Maybe they will. And but so you and oh, am I? He's trying to show me the time. No, okay. Okay, I'm just gonna keep going. Okay. All right, thanks. So we split apart the dedicated outside air system into two pieces. And so the usually like a VRF unit is, onto a DX coil that's attached to this unit. And it it does the dehumidification process using a VRF system. So there is some field installed stuff, so it's a little bit harder to install in the field, and there is the possibility of more leaks. It's not a lot more refrigerant, but it is a little bit more refrigerant. But these systems are really good at low temperature performance, whereas the package systems aren't quite as good. So as you get colder, these become better and better than the package systems. The third system is a geothermal system, packaged geothermal. So this has a lot of benefits of the first system, and it's for plugging into it. If you're already using geothermal for your heating and cooling, use it for dehumidification. And this is just another variation of that, where you split it apart. You use a really high performance ERV, and then use the geothermal water to water unit to and these systems, they perform really well. And then there's the wall mounted or room by room dehumidifiers, and these are simpler because they don't have any ductwork, so you're getting rid of a lot of the you just don't need all that ductwork through your ductwork, smoke dampers, all that crazy stuff. You can get rid of that and use if you're using like an EPOCA system, then you've really simplified your system. But as seen in this next graph, they aren't quite as efficient because they're central systems are often have the benefit of using you get the economy of scale with a big unit, and you can get some really good efficiencies. So on the left is the energy use intensity of adding dehumidification for 1 year. So packaged dedicated outside air system, decent. The split system is better. About, in this climate, it was about 15% better, and most of that energy actually was in low temperature. Like none of it came from cooling at all. It's all in the the defrost cycles, and because VRF doesn't, VRF can operate really low temperatures, whereas the packaged dedicated outside air systems can't really do that. So they rely on the electric heat a little bit more. Packaged geothermal does really good. Split is even better. And the wall dehumidifiers kind of coming in the middle. And that is because they're only treating the room. They're treating things at the, they're watching the humidity in the room. So they're just not dehumidifying quite as much. And so it's more about controls than it is about actual efficiency of the units. So even though they're a little less efficient because they're just a little tiny thing sitting in everybody's apartment, they get that benefit of, they're not dehumidifying when they don't have to, because a packaged system on the roof definitely does. It doesn't always, it can't always hit exactly the right spot. So when you're talking about carbon, in a dirty grid like Pittsburgh, it follows the operational energy pretty closely, and you don't really see any differences until you get to a really clean grid where you start to see the refrigerant popping into the pie a little bit more, and you start to see that the decisions you make about how much refrigerant you put in the system do have an impact, but you really can't see it until you get to a clean grid. So it kind of gets more pronounced, but you can see that the package dedicated outside air system actually ended up a little bit less carbon impact than the more efficient dedicated outside air system, which was a really interesting thing to see that refrigerant, the red refrigerant line kind of starting to be more pronounced. Oh yes, of course. Yellow is operational, red is refrigerant, and blue is embodied. And the embodied, they're all basically the same because they're central systems on the embodied side of the equipment, but except for the wall dehumidifiers, because there's just so much less ductwork, so there's so much less insulation, and you actually see a little bit there, but it's not the biggest thing. So yeah, I think I went all over all of this. The package dedicated outside air system was used because they are the cheapest and they're the simplest as well. If you don't need to have, the commissioning is very easy. All of that stuff is very easy. The roof penetrations are all easy, which is also good for passive house. So that's why we went with that for this building. And the EPOCAs didn't exist yet, so couldn't really use those yet. Because this was in design probably 5 years ago, so that does affect some of the things we did for this project. And to the new mainstream, I think we've gotten, so on domestic water heat pumps, I think we're starting to get into I think we're starting to get past early adopter and heading into early, gosh, oh man, I just blanked. The early majority. We're getting into the early majority because I've been hearing a bunch of people called me up and said, hey, they were talking about carbon dioxide refrigerant at Greenbuild. And I was like, yes, we've gotten past the early adopter phase. So that's great. So the first system we analyzed was distributed tanks, and these have been around for the longest time. Well, out of all the heat pumps, these have been around the longest. So this was actually the only system we actually had at the time to do heat pump hot water heating in for this building. But it's relatively simple because you don't have a circulation loop or anything like that. It's just a heat pump per 1 or 2 apartments, and it's a package unit. Doesn't use a ton of refrigerant, and doesn't leak a whole lot. So the first of the central systems is this one's kind of our personal favorite right now. We're doing a lot of these because oh, Swegon is not the right word there. That's a sand CO, that's the sand CO2 from Sandon. And these, I mean, Sandon was the first one to get the CO2 heat pumps to this country, and we thank them for it, because the CO2 really does a good job of heating hot water. It's a really good refrigerant for heating hot water. It has its limitations and it has its little quirks, but it does a really good job. So this is kind of the first system is kind of a hybrid system. So you use the Sandins to use the CO2 heat pumps to heat up the bulk of the hot water, because they want to see a really high delta T. What that means is they want to see 45-degree water coming in, and they want to see 140, 160 water coming out, which is very unusual for a heat pump, and that's why CO2 is kind of a fun refrigerant. Doesn't work very well for cooling at all, but for heating hot water, it's fantastic. So, the limitation with the CO2 heat pumps is that they don't want to see the recirculation water. And when you use a central system, you need recirculation water. You can't just let the water get cold in those pipes. You need to move it around. They have smarter ones now where they actually like learn from the building. So that's pretty awesome. And so, we can minimize the energy of the recirculation loop. There's a bunch of strategies for that. That's a whole presentation in itself. But we have to heat that water back up, because that water comes back at 95, 100 degrees. We got to heat that back up to 120. And so the best way that we've found to do that is use one of these tank type heat pump water heaters, and just let that thing handle the recirculation load, and let the Sandins handle the bulk of the hot water heating. Let those different heat pumps do what they do best. And the other way to do it is not to use a heat pump for that recirculation load, and use electric resistance. And this is the system used that is like the standard Sandin system. This is going to be initially what Mitsubishi also recommends for their brand new system. And we're going to try and get them to use a heat pump for that recirculation load too. And I really apologize about putting Swegon in there, because that's not who it is. Central geothermal, another variation on the theme, but this is I mean, you're using your geothermal loop that you've already got from heating and cooling, and you add to it with your hot water. And that's pretty much how these work. There's a few moving parts in them, but not any more than this, not any more than any other central system. The most complicated and not well known system is using VRF to heat hot water, and there's actually a secondary compressor that heats the hot water, and you have a VRF compressor on the roof, and you have a secondary compressor down in your mechanical room that heats the hot water. And these systems are complicated. These are and not many manufacturers do it. Like Mitsubishi pulled theirs out of the American market, so they don't do it anymore. So there's only a few people that make it, and so it becomes tricky to manage that, because you don't want if you've got a VRF system on your building, you don't want to have two different VRF manufacturers. That's just nonsense. But these systems are a little bit complicated, and they're VRF, so they come with their refrigerant problems. They come with a lot more refrigerant, there's different refrigerants. So you get different. There's some limitations to this, and it doesn't do as good on energy anyway, because you have that secondary compressor. So all of these numbers are really good. I don't want to say that any of these systems are really a whole lot better than any others. In fact, it's hard to tell if any of them actually are. So if you look on the graph on the left for the energy use for a given year, they're all pretty much neck and neck. And the little differences are like, so the yellow is just the bulk hot water heating, and then the red is for the recirculation heating. So you can shave that off by using a heat pump, but these are all really good systems. These all perform really well. Even the VRF is not, it's not a terrible system by any stretch of the imagination, but it's yeah, so they're all really good. I don't want to discourage you from using any of these, but you can see the carbon impacts with the current grid are tracking along with the operational energy, just like they did in all the others. And you can, there's very little variance in all of them. And you know, depending on how cold your climate is, will affect these a little bit more. So the colder you get, the more energy you're going to use for all the different systems. But certain ones will do better than others with the colder climates. And then when you get to a cleaner grid, you can, you know, it really, these systems are all really evenly, they're all very good. So they're all doing well in refrigerant and in operational. So you can't really go wrong with heat pump hot water. That's pretty much the the takeaway from this. Oh, and I put this in right at the last second. So this is for 20 gallons per day, which is not the passive house standard. The passive house standard is 6.6 gallons per day per person. And so what we've found is that in like family buildings, people use a lot more than 6.6 gallons per day. But in senior buildings, they do use about 6.6 gallons per day. It's actually kind of when we actually measure it, it's kind of amazing that it's that low. I don't know where that number came from. I don't know if it came from Europe or from senior housing. It could have been either. So the refrigerant and the recirculation are just more pronounced in when you use less water. You're recirculating the same amount, but it's a bigger piece of your energy pie. So I thought this was really cool to put this in, because you start to see the recirculation energy and how the different systems do on the recirculation energy, which is interesting to see. Carbon impacts, you can see them on the graphs. There's, you know, all the heat pumps still do really good. So I don't want to discourage any certain types. There's definitely a place for all these different types. And I mean, a lot of it has to do with your building. If you have enough room for distributed, you know, that's a good type, but not all buildings have room. A lot of urban, like really, really dense urban buildings don't have room for distributed heat pumps. And you wouldn't want that many distributed heat pumps in a building anyway, because it's just a kind of a maintenance hassle. So then central systems become a really nice option. Yeah, I already mentioned that the VRF is a bit complex, but it doesn't have any freeze protection issues, because there's a VRF unit on the roof that will never freeze. Whereas all the carbon dioxide based heat pumps they put actual water up onto the roof. So normally the freeze protection isn't an issue, because when the units are on, they are managing that themselves. But if you lose power, you got to be careful. So you have to provide ways of making it so those machines don't freeze up on the roof. And distributed tank type hot water heaters don't have that problem either. But you have to figure out how to duct them. You have to duct them to somewhere, because a mechanical closet doesn't have enough. It doesn't have enough heating energy in it to because they're putting out a third of a ton of cooling when they're operating. So you have to find a place to put that. And and the warmer the climates go, that becomes easier. But so you have to either put it back into your ventilation area if you've got a central ventilation system, or you can put it into the rooms, which you get free cooling in the summertime, but you also get free cooling in the winter time, which isn't ideal. So so there's trade-offs, and you can see from the energy it doesn't affect it a lot, but each situation is going to be different for these. So that's it. I kind of rushed through, but bring on the questions.